In section 2.5, we'll be looking at the notations for the first derivative, interpreting the meaning of the first derivative in the context of a scenario, and what do the first and second derivative tell us about a function. So given y equals f of x, we can write the derivative as f prime of x. And remember, the derivative means the slope at a particular point. There's a second notation that we use. It's called dy dx. The second notation was introduced by Wilhelm Gottfried Leibniz. And he was a German mathematician. And the d stands for small difference in. So when we look at dy dx, we're really looking at a small difference in y values over a small difference in x values. We say the derivative of y with respect to x. So later on we'll look at ds dt. That would be the derivative of s with respect to t. All right, let's take a look at an example of, again, using the definition of derivative to find a formula for dy dx. If you recall, in a previous section, we found the derivative at a particular point. So say at x equals 2. Here we're going to find a formula for the slope, and then we can use any x value in the domain to find the slope at a particular point. So our function is y equals x squared minus x. And remember, dy dx is the same as f prime of x. And using the definition of derivative, that's our limit definition. So we want the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so first thing we have to do is find f of x plus h. So that's x plus h, quantity squared, minus x plus h. So I'm just going to put that in some brackets there to highlight that. So that is f of x plus h. I've substituted x plus h into x in the function. Then we're going to subtract f of x, which is x squared minus x. I would be careful using parentheses so that we don't lose the negative being distributed over the quantity. All right, simplifying what's in these red brackets, let's expand the binomial x squared plus 2xh plus h squared minus x minus h. Again, I'm going to keep that in red parentheses, red square brackets, just to indicate that is f of x plus h. Now you may have figured out from previous problems where you're finding the derivative, the function will always disappear because we're going to subtract the function from f of x plus h. Well, there's an x squared. That's going to disappear. There's a minus x minus a minus x. That's going to disappear. All right, simplifying what we have 2xh plus h squared minus h all over h. Notice every term in the numerator has a factor of h, which will be reduced with the factor in the denominator. So if I factor out of h, I'll get 2x plus h minus 1 over h. Factors of h reduce. I now can let x or h go to 0. Letting h go to 0 means that this term zeroes out, and we're left with f prime of x, or dy over dx, the derivative of y with respect to x, is 2x plus 1. Okay, so for this function, which is a parabola, right, we could find the slope at any particular place. For example, if I wanted the slope at 0, 0, which is a point on the graph, I plug 0 in to the derivative function, and f prime of 0 is 1. So the slope of this function at x equals, or the point 0, 0, is 1. All right. So if we wanted to find the derivative at a particular x value, actually let me go back to that slide and I'll just use the notation that was given. So I could say, what is the derivative of y with respect to x at, I'll choose another point, at x equals -1. Oh, well, I'll just do x equals 1. All right, so we will take our derivative function, evaluate it at 1, we will get a slope of 3. So on this curve, when x equals 1, the slope is 3. We could also evaluate the point, 1f of 1, which is the point 1, 0. Okay, so when we look at this next slide, this will look familiar. If you want to find the derivative at x equals 2, you can also write f prime of 2, or the derivative of y with respect to x, and this bar means evaluate at x equals 2. All right, suppose s, oftentimes we refer to s as position, equals f of t. S is a function of time. And s gives the distance in meters of a body from a fixed point as a function of time in seconds. So remember, we're talking about some function, right? T f of t or t s of t. And the units for this would be seconds and meters. Okay. All right, so when we describe the following real-world expression, the derivative of s with respect to t at time t equals 2, we would say at time t equals 2 seconds, the body, right, it's just some object, the body is moving at a velocity, right? Because remember the derivative is velocity. And it's moving at a velocity of ds dt meters per second. Okay, what are the units associated with this quantity? Well, that's meters per second. Right, you're talking about the slope, so the change in s over the change in t. All right, what is the common term for ds dt? Common term is instantaneous velocity. What is the real-world meaning of f prime of 2 equals 10? So here they're giving us the example that at 2 seconds, the instantaneous velocity is 10 meters per second. Okay, so the body at time t equals 2 seconds has an instantaneous velocity of 10, and that's a positive 10, meters per second. So if you recall, when the velocity or the derivative is positive, right, what does it mean about this body relative to the fixed point? Well, since the derivative is positive, ds dt is greater than 0, it means that this body is moving away from the fixed point, right? The distance between the body and the fixed point is increasing. All right, example number 3. The cost C in dollars of building a house, A feet squared, in area is given by the function C equals f of A. So oftentimes when I start these problems, I just like to say, what are we talking about in terms of a regular old point on this function? So the input is A, and that's A feet squared. And the output is cost C in dollars. Okay? So if you think about a slope for this function, right, slope of a secant, for example, between 2 points, we'd be looking at a change in cost over change in area, right? So that's a change in dollars over a change in feet squared. So function, feet squared, dollars, slope, dollars per feet squared. All right, so question A, what is the real world meaning of f of 2,000 is 195,000? And using units in your answer would be helpful. All right, well, the input is 2,000, so that means that you're building a house of 2,000 square feet. The output, 195,000, is actually in dollars. So this is feet squared, this is dollars. All right, so we'd probably just say it costs $195,000 to build a 2,000 square foot house. What is the independent variable? That would be the input. So that's A in feet squared. What is the dependent variable? That'd be cost in dollars. Okay, what is the sign of f prime of A and why? Okay, so if you're building a 2,000 square foot home and it costs $195,000, what would you expect to happen with a 3,000 square foot home? Would you expect the cost to be more or less than $195,000? Probably more. So we would say that as cost or as area increases, as the area of the house you build increases, the cost will also increase. Therefore, f prime of A will be a positive value. Okay, or we could say d of C, the derivative of cost with respect to area, is greater than 0. Okay, write the Leibniz notation for f prime of A. And I've actually done that right here. So f prime of A equals d of C, derivative of cost with respect to area, dc over dA. What are the units? F prime of 2,000. So remember, that's a slope, and slope will give us change in cost over change in area.